Board.
Oh, I just ordered a whiteboard because I went back to San Jose and I wanted to use this whiteboard to run my office hours and uh yeah I just like using the whiteboard because I know some people prefer the whiteboard over the iPad, but sometimes I will still use the iPad as well.
Mm. I also got myself a whiteboard, but it's like a planner whiteboard.
Oh
It just has
yeah.
like the dates and like not a date, but like it's just like month, and then there's just a calendar there.
Uh-huh. And then you
Yeah,
use that to put your to-do list in there and like to do stuff
yeah.
in
What I
there.
want to do for July.
Uh-huh. Oh, that's good. What have you put in that planner so far?
Oh, right now, I mean, I like reorganized my entire room, and now like it's very neat and like it's very I think it's like I can use it for studying now, but like
Uh-huh.
for like planning, all I did was like clean, and like I read like 30 pages of a book
Oh
because
yeah,
that's my
oh
summer homework. So
I see. Dang. Summer homework for AP Lang, AP Lit,
yeah,
that class you're taking?
just AP Lang and then um AP Chem. But right now, I'm just trying to focus on finishing this book first.
I see, I see. Yeah.
I'm not. Do you like reading books or nah?
Um, I am currently reading uh these books right now. This one and this one.
Mm,
Just to like build up my ochem like tutoring business and get more like people how to advertise better, how to make the offer better and stuff like that. Like make content, paid ads,
mhm,
referrals and stuff like that, you know?
mhm.
Yeah. Right. What do you like reading books or
I'm forcing myself to read so I can improve my attention span.
yeah, like not the TikTok doom scrolling and stuff like that.
Yeah.
Uh-huh. How has the your sleep schedule been? Like have you made any changes to it?
Yeah, it's
Um,
a lot better. I see
uh-huh.
the bags under my eyes getting less and less every day.
Yeah, that's good. That's good. Recovering from the uh, sleep deprivation.
Mhm.
Yeah.
I don't wait, so school ended for you, right?
Yeah, it ended for me. But I'm gonna start my chiropractic school um in like 2 weeks. Like it starts July 8th. The orientation is July 5th, but chiropractic school starts July 8th.
Mm. So, do you got the whiteboard for like chiropractor school or
Yeah,
is it
yeah. I'm gonna use it for anatomy too and chiropractic school as well.
mm,
Yeah. And I think it's gonna help me because like I'm gonna just gonna keep writing it down until I remember it. And also understand it as well, like not just remember it, like and make the connections as well.
that's good. I
Yeah,
already have like two whiteboards in my own home, but like now I'm gonna start using it.
yeah, that's good. How's your sleep schedule been? Like what time do you sleep now? And what time do you wake up
Ideally
now?
it would have been 10 and then I go wake up at 6 because my dad wants me to do something like every single day.
Oh, yeah. I just finished eating dinner because my parents like make dinner like kind of late, and then like I just got up here after dinner.
Hmm.
Yeah, I wish I could have started earlier, so then like we could sleep earlier, but then yeah, I eat dinner pretty late now at San Jose.
Oh. Hmm.
Yeah.
I'd say I finished eating dinner by 6 and then because I probably just eat pretty early.
Oh, you finished eating right by 6?
Yeah.
I see, I see, I see. I'm just testing this. Okay. Are you able to see this clearly?
Mhm.
Okay, okay, that's good, that's good. Let's see. Hey Joseph, do you have any questions so far?
Tiffany and I were thinking of doing practice exams on Booster.
Booster? Oh yeah, we could do that.
Okay.
Yeah.
Wait, but you're gonna do it on the whiteboard or
Uh, should do you prefer the whiteboard or the iPad?
I mean if we're gonna share screen, then I think it's better if it's on the iPad.
On the iPad?
But
Okay, okay.
let's actually for this session, let's keep the
Uh-huh.
whiteboard and see how
Yeah, I
it
see.
is.
Yeah, I see how it is. Just send me the screenshot on Discord of the problem, and then I'll look at it through here and then write it on the whiteboard. Yeah, Joseph is a pre-dental student. He's studying for the DAT again. He's taking his DAT July 8th. Yeah.
I'm studying for my driver's license. That's like coming up in 3 days.
Oh, driver license test?
Yep.
Wait, is it the permit test or the actual like on the wheel
Actual
driver
like
license
bond,
test?
not the actual test, but like I'm going to bond driving school if you ever heard of it.
Bond driving school. Oh no, I haven't heard of that.
Just a driving school for like there's like 3 lessons and the total of it is like $600.
Oh, I see. And it's not like the actual like DMV test, right? It's like just the test for their school to test if you're like ready for it.
Yep.
I see. Have you been on the road before, like with an instructor or a supervisor?
No, I've only been on like the road twice.
Uh,
My dad.
with your dad, I see.
Yeah, no accidents, no hitting vehicles whatsoever, so that's good.
Yeah, that's good. Like once you get a license and you get a car, like you get so much freedom. Like you get to go anywhere you want. Yeah. But like, you're still living with your parents, so like they might not let you like go out like whenever you want. Yeah. Yeah. Joseph and Tiffany, when you guys have the problem, just send it to me on the Discord, and then I'll put it on the whiteboard here.
Okay.
Tiffany, you pull up the questions since you're the one who did the exams.
Bro, my score is so bad though. Oh, okay.
You guys tried the ochem bootcamp like section practice for the bootcamp thing?
So I've been doing practice test I've been doing it for a long time, so I'm just pulling up like a bunch of practice test questions. Yeah, because they're more targeted for DAT specifically.
Yeah, that's good.
And I think it will save you some work to like having to search up problems.
Yeah.
Do I just
Yeah, let me make it so people can share screen. Okay, there you go. Anyone can share screen now. Okay, I see. Okay. So, is it the first one? Why is CH3CO CH2F more acidic than CH3CO CH3? Like, you got that right. Do you need any further explanation on that, or like what question do you need explanation on?
Joseph, you need help with this or no? Because I don't need help with this one, but if Joseph needed, then
yeah.
I think I'm okay.
Okay. Tell me which one like you need help on, maybe. Maybe let me see. This one I'm not too sure how the radical reactions work because I forgot how it went. So maybe you can pull up like an example of a radical reactions.
Yeah, and these are testing the conceptual questions like the highest activation energy, initial.
Yeah, just guess on this one.
Of the free radical thing. The activation energy relation is equal to the termination step. I see. Yeah, I'll show you like the overall process of it and like the conceptual things as well. So for free radical halogenation, right? I'm going to show you the general equation of it, and then the mechanism, and then the activation energy, and some other concepts on that as well. So free radical halogenation, you're going to have a carbon attached to some hydrogen reacting with X2, where X can be fluorine, chlorine, bromine, and you're going to have that under light, HV, or heat. And what that's going to do is replace this hydrogen here with a halogen, CX, right? And there are three steps for this mechanism: initiation, propagation, and termination, where for the initiation step, a heterolytic cleavage is going to happen where that bond right there represents two electrons. One of the electrons is going to go onto that halogen right there. The other electron of that bond is going to go to the other halogen right there. And that's going to give us our two radical halogens here, right? That's the initiation step. All initiation steps always start with 0 radicals, and they always end with like a radical or 2 radicals, right? So initiation step, coming from 0 radicals to 2 radicals, right? That's starting the radical chain. There are 2 parts for propagation. I'm gonna call that part A and part B, right? Oh yeah, you could also stop sharing your screen so then the Zoom can record the big whiteboard quicker. I think I have the question.
Oh, okay. Okay.
Yeah. Yeah. And also for part A, right? Let's just say I use an example as CH4, right? Let's do CH4 really quick. So that means this is going to be, let's say, HGCH. That's going to be HGCCX right here. Okay. I'm going to bring in that alkane, the RX, and the radical halogen that I created in the first initiation step here. This radical here is going to make a bond with this hydrogen here, right? Where this bond between the carbon and hydrogen has 2 electrons. One of the electrons is going to go make a bond with that halogen right there. The other electron is going to make a radical on that carbon right there. And that's going to give us this radical here, that R radical. And our side product would be HX, right? Where this new bond between H and X comes from these 2 electrons, 1 electron here and another electron there. So that's propagation step A. For propagation step B, right, we're going to bring in this radical that we just formed here and use another X2. Because think of this X2 as an excess. We have a lot of them in solution, right? This R radical here is going to make a bond with that halogen right there, right? And then this electron is going to go to make another radical on that halogen right there. And that's going to give us our major desired product, this halogenated alkane right here, plus an X radical, right? So for all propagation steps, we're always going to come from 1 radical and end with another radical, right? And that propagates the chain. It keeps the chain going because we have another radical here that can come back and keep reacting with the other step. We have a radical here that can keep reacting with the other step here. But initiation step, we start the radical chain. We came from 0 radicals and we start with 2 radicals, right? The reason why I didn't react this radical with another X radical is because when we bring 2 radicals together, that makes 0 radicals. And that's the termination step, where there are a lot of termination steps, right? Because in termination steps, you're going to bring in any 2 radicals together to end the radical chain, to form 0 radicals. So we could have these radicals come together, we could have these radicals come together, or we could have these radicals come together, right? And combine to end the radical chain, terminate the radical chain. this would just create X2. This would create the desired product, the halogenated alkane. This would create an undesired product. Or you can see this as C H3 CH3 or C2 H6. Right. That is not what we want in the equation here. Right. So termination. We're terminating the radical chain by coming from 2 radicals and ending in 0 radicals here. Right. Initiation, 0 radicals to 2 radicals, that starts the radical chain. Propagation, 1 radical to another radical, that propagates the radical chain. It creates radicals that can keep the reaction going and going and going until the termination step, where 2 radicals come together and stops the radical chain. Right. Where propagation happens 1,000 times more than initiation and termination steps, right? Propagation is the major thing that's happening here. Initiation and termination steps rarely happens. Where you notice how for the initiation step here, we broke that bond to create 2 radicals. That bond breaks coming from the energy from light or heat. The light or heat comes down and breaks that bond right there, making this reaction have the highest activation energy because it needs that energy to create these radicals here, which is what the DAT was asking for. Which one of these steps has the highest activation energy, which is this initiation step here, which requires the most amount of energy to break the bond and create 2 radicals here. So that was the question. But in case they ask anything else for this reaction, these might be useful concepts as well.
So in terms of stability, does it matter where the radical locate on the compound?
Oh, in terms of stability, yes, it would, depending on what your alkane is. In this alkane here, we only had 1 carbon, so that was only that was the only choice, only 1 carbon for it to go. But if we have something like this right here, let me see. I'm gonna erase this. Do you need this still? Or actually, let me just screenshot this so then I can post this on the notes afterwards. Yeah.
Okay, thank you.
And then I'll show you examples where it does matter. Sure. Okay. See. Do you need this board still?
No, I already took a picture of it too.
Okay. Yeah. Oh shoot! I just realized I didn't have to erase this. It's okay. I'm learning. I just got this board today. I could have just. Oh my god! I'll do that next time. I could have just done this and then go back to that board later, and then use this board instead. Right
Oh.
Okay. It's okay. I'll do that next time. So for this one right here, sometimes it does that. Sorry. Okay. So let's see, depending on the halogen you have, just use this one instead. And let's say the carbon it prefers. This is the general case here. So generally, fluorine prefers to go on a primary carbon. Chlorine prefers to be in a secondary carbon. Bromine prefers to be in a tertiary carbon. So if we have something like this, and then we react this with the halogenation reaction, like Cl2, like Br2, like, oh shoot, fluorine. Because fluorine, I barely use in synthesis, but fluorine is still a thing. Cl2, Br2, like fluorine, we said it prefers to be in a primary position, so it could either be this, or this position here. But what do you think it's going to be on? Because which one of these positions are the same because of symmetry here? Let's say this is A, B, C. Two of these are the exact same because of symmetry, like, or not the exact same, but the same chemical environment. Like think about for H and MR, like which one of these would have the same peak?
A and B.
Yeah, A and B, right? Because A and B have the same environment. Because we see that this bond right here is a single bond that can do free rotation, and then when we rotate it, this A and B can rotate into each other's spots, right? Where A and B together, they have 6 hydrogens, whereas C, they only have 3 hydrogens. So fluorine would prefer to be in either A or B. It doesn't matter. It's the same thing. Right? Chlorine would prefer to be in the secondary position, which the only secondary position we have is this carbon right here. So chlorine would be right there. And then bromine, tertiary position, only one tertiary position, which is that tertiary position right there. Right? So this is the general case right here.
So overall, like, what about like in general, if you have like a structure, and then, because I remember one of the question was asking in general which radical would be the most stable, and then they give you like a tertiary, secondary, and allylic and primary.
Oh,
So
yeah.
for
Yeah, so that's a different kind of question where they're asking about the stability of radicals and carbocations, which is the same thing. That's good. You said allylic as well. So in general, stability of radicals, which is going to be the same stability principles as for carbocations. Right. So the least stable is going to be like a CH4 radical or carbocation, and then primary, and then let's say secondary, which is about the same as primary allylic. It's kind of iffy because this is still a carbocation that's on a primary carbon, but it's allylic, so it could do resonance, and resonance makes things more stable. And then it's going to be, let's say, tertiary carbocation, which is less stable than secondary allylic, which is less stable than this tertiary carbocation that is also allylic right here. Right? You can replace these carbocations with radicals as well, and it's going to be the same thing. So when it can do resonance, it increases the stability of the radical or carbocation.
Oh, so resonance kind of like overpowered the tertiary.
Hyperconjugation. Yeah. Resonance overpower hyperconjugation.
Is that like a reason for that?
Yeah, the reason is because if charges are able to move around more in the molecule, more delocalized, it is more stable. Think of it as like it's able to move more, breathe more, right? Because we see that we could do resonance here, resonance here, resonance there. And when we draw out the resonance structures, you know how the positive charge will end up on that carbon, the positive charge will end up on that carbon right there. Like the charges are actually moving. Whereas this charge right here at the tertiary carbon, there's no resonance going on. There's no double bond. There's no pairs of electrons going on. So it's stuck there. It's localized there. It's suffocated. It can't breathe as much, right? But that's why it's stuck there. If it could move more around the molecule, because if we draw out the hybrid form of this, electrons are moving like that. And if it's able to move, move more, it's more stable.
Okay.
This one here, it can't move at all. It's stuck there. So secondary allylic is more stable than tertiary, right? But tertiary allylic is more stable than secondary allylic. Right? That allylic there makes it more stable because of resonance.
Okay.
Screenshot this. So any more questions on this?
If not, then I can go over the other questions that I saw in the practice test.
Yeah. You can share your screen again, and then I'll write it on the board, and then you can stop sharing it when I go over it.
Okay. So for this one, like, yeah, I'm not sure. Like, I just don't remember what was this reactions.
Oh, okay. I'll go over this. I'll go over this reaction. Leave it on the screen for now, and I'll write it on the board, and then I'll go over it. And then when I go over it, the reaction might come up. Right. Okay. So you can stop sharing, and then I'll go over this question. The first thing I like to do is I like to draw out this condensed formula into a bond line formula. So we have CH3, CH2, CH2, CH, Br, CH3, which looks like this, right? Do you have any questions on how I got to this point so far?
No, I'm good with that.
Okay, that's good. So now I'm gonna also draw out the reagent in bond line form. Whenever you see potassium or sodium, what charge does that come with always?
Negative charge?
Negative charge, right? So that means that whatever is attached to it is, oh, right. So the potassium and sodium is positive charge, and whatever
yeah,
is attached to it is a negative charge, right? So that oxygen there has a negative charge right there, and this is CH3, CO minus, right? This is the 3 CH3s on that C with the O minus right there, right? Now, is this a strong base or a weak base? Do you remember if this is a strong base or a weak base?
It's a weak base.
Right, so if you see a negative charge on an oxygen or nitrogen, right? Negative charge on oxygen or nitrogen, think of that as a strong base.
Oh, and then it's a weak acid because it doesn't wanna donate the negative charge. Is that it?
So this is a strong base, weak acid, because the hydrogens here don't want to get deprotonated, because when we deprotonate one of these hydrogens here, we get that conjugate base right there, right? And you know how in our last session we said acidity increases when the conjugate base is more stable? Is this conjugate base stable next to that negative charge right there?
No.
No, right. So that means that this is a weak acid because the conjugate base is weak, right? That's the thing you look for acidity, the conjugate base. For basicity, right? You don't look at the conjugate base. You look at the stability of the negative charge here. This negative charge here, you notice how it's like on an oxygen, it can't do resonance at all. this is a strong base because it's stuck there, and the oxygen really wants to grab a hydrogen to become neutral. It wants to grab a hydrogen to become an alcohol. Right? Because if this is a strong base, it wants to grab a hydrogen, and when it grabs a hydrogen, it becomes neutral and stable. Right? And is this a bulky base or a small base here?
Bulky.
Yeah, bulky base because of the third butyl. So what kind of substrate do we have here? Like what kind of haloalkane? Is this a primary, secondary, or tertiary haloalkane? How many other carbons is this carbon attached to? The carbon that is holding the good leaving group here. This is a good leaving group. How many other carbons is this carbon attached to?
2. So
yeah.
Secondary.
Secondary, right? Secondary substrate. When we have a secondary substrate, strong base, strong nucleophile, this is going to be E2 reaction. Right? Where in E2 reactions, we are always going to form a double bond. But because we have a bulky base, we're going to look for the Hoffman product. Right? So the first thing you do for this E2 reaction is find your beta carbons. This is going to be your alpha carbon right there, the carbon holding the leaving group. The beta carbon is going to be the carbons attached to the alpha carbon, right? And I'm going to draw out one hydrogen for each beta carbon. One hydrogen there, one hydrogen here, right? So which beta carbon would create the more stable double bond? Like if I grab this hydrogen here, make a double bond there, kick out the leaving group, right? Which one would make the more stable double bond? Grab that one, make a double bond there, kick that out. So this also tests about like double bond stability as well, kinda.
The left one.
Yeah, the left one, right? Because this base here, if it goes and grabs that hydrogen right there, makes a double bond here, kicks that leaving group out, that double bond is di-substituted. It's attached to 2 other R groups, 1, 2. If we grab this hydrogen here, make a double bond here, kick that leaving group out, this is mono-substituted alkene because there's only 1 R group right there, right? So we prefer to get this left one here, right? But what's the problem here? Why can't we do that in this example here? What's wrong with the base? Why can't this base grab that hydrogen right there?
Because it's too bulky.
Yeah, too bulky. Not enough space to reach that preferred hydrogen. It could only grab the hydrogen that is the most available, the one that has the most space to grab because it's bulky, Hoffman. If it was like not bulky, right? It was like a small, strong base, then you would go for the Zaitsev alkene, which is the more stable alkene. So you'd grab this one. But because our base is bulky, we're going to grab the most available hydrogen, make a double bond there, kick the leaving group out, and get our final answer here. Right? This mono-substituted alkene and the side product alcohol, right? Where that O grab the H, which this H is that H of the alcohol right there. So this was a E2 reaction here.
Sorry, can you explain how you're able to determine the strong base and strong acid? Because I'm so bad at that still.
Oh yeah. So when you see a negative charge on an oxygen or nitrogen, always think of that as a strong base, right? A negative charge on oxygen or nitrogen, that's always a strong base. The bulky strong bases, there's only 2 that you need to know. This is one of it, the tert butoxide, the CH3COK or CH3CONA, and the other one, you might see that as LDA, or you might see it in this form here. Well, most likely you see it as LDA. This is very bulky as well. Whenever you see that or LDA, always think of E2 reaction, Hoffman. Right? Let's see. For strong acids, that's a different concept, which we could go over in a different board because that's not related to this reaction here. Because strong acids is going to talk about the conjugate bases, and then the conjugate base stability will depend on this acronym here, CARIO. where this is going to be charge, this is going to be atom size, resonance, induction, and orbital or hybridization. Remember how we went over that in that last session? Do you want to go over this again, like this whole acid acronym, like the strength of the acidity?
I got this.
Uh-huh.
I'm just still bad at determining, like looking at the reactions and see which one is like E1, E2, and SN1, SN2.
Yeah, let me give you different practice problems on SN2, SN1, E1, E2, and then have you try it.
Yeah, can you have them like side by side so I can see like the actual
difference?
Yeah.
Yeah, I'll show you the side by side difference. Okay. Okay, try these problems here, and then let me know what you think about it, and then I'll walk you through these problems here. Like what your thought process is.
Oh, do you want me to work through it first or just tell you the thought process?
Yeah, work through it and tell me your thought process at the same time.
So I think the first one, PMSO, is that a bulky? And
Oh, okay. Before we go over these problems, all right, let me go over like all the types of nucleophiles that you see for these reactions: SN2, E2, SN1, E1, like strong base, weak base, bulky, unbulky, weak base, weak, strong nucleophile, weak base, weak nucleophile. Like, let me go over that first, and then go over this problem here, and we can go back and forth. Yeah, and then also like what kind of substrate it is, and then what kind of reaction would it be depending on the substrate as well. Yeah. Okay, let's go with that. Over here. Okay. So the easiest thing to remember is the weak base, weak nucleophile. Weak base, weak nucleophile. That's going to be mostly two things that you see. It's going to be water and alcohol, right? Where R can be any random hydrocarbon chain. It could be CH3OH, it could be CH3CH2OH. If you see any of these neutral water or alcohol molecules, then that's a weak base, weak nucleophile. A weak base, strong nucleophile would be things like CN minus, N3 minus. You can also see say SH minus, RS minus, like any of these random letters. It could also be, no, not N, but neutral, ammonia. Right. The most common ones will probably be CN minus or N3 minus, and you'll most likely see them as NaCN, KCN, or NaN3 or KN3. Right. The strong base, strong nucleophiles, there's two types of them. There's unhindered and there's hindered. Right. We already went over the two types of hindered bases, right? Which is going to be turbotoxide. You don't have to see potassium. You can also see sodium, like Na instead of K, or you can see LDA. Right. Those are the two bulky bases there. The unhindered bases would be like any other thing, any other oxygen or nitrogen with a negative charge. So some examples would be like CH3OK, CH3CH2ONA. It could be CH3 CH2 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 NH minus or K. Right. Like this structure here, 1 2 3 4 5, 2 3 4 5, 1 2 3 4 5, and H minus. This is considered unhindered base because this chain right here is just gonna like float away in the solution, right? These here are considered hindered bases because you notice how the carbon there that is near the O minus, it has like other groups attached to it. It has like this carbon here has 3 groups attached to it. Like these carbons here has 2 groups attached to it. But if we look at this carbon here attached to the nitrogen, there's only 1 group attached to it, where that 1 group can just like float away in the solution. But if you have something like that, right, then that would be considered a hindered base. But in this case, we don't have that. So this is an unhindered base here. Okay. Okay, so those are the types of weak base, weak nucleophile, water or alcohol, weak base, strong nucleophile, NaCN or NaN3, the types of strong base, strong nucleophiles, when you see negative charge on oxygen or nitrogen, and there's 2 types of them, unhindered or hindered. Now let's go over the substrates. If it's methyl, primary, unhindered, primary, hindered, secondary, tertiary, and what kind of reaction it would give you. Okay. Let's see. We could do it. How do I do? Okay, I'll just do it from here. Weak base, weak nucleophile. If you see this reacting with this is gonna be a more simplified example case because I don't think the DAT will test like the primary unhindered methyl versus primary hindered. So I'm just gonna do a primary, secondary, and tertiary because I don't think they'll go over primary unhindered versus primary hindered substrate. Okay. This is gonna be no reaction. Secondary is going to be SN1 or E1. They always go together. Tertiary, that's always SN1 or E1. They always go together. Right. For the weak base strong nucleophile, primary, SN2. Secondary, SN2. Tertiary, no reaction. For the unhindered, primary, SN2. Secondary, E2. Zaitsev. Tertiary, E2. Zaitsev. Right. For the hindered, primary, SN2, secondary, E2, Hoffman. Because it's bulky, going for the less stable alkene. Tertiary, E2, also Hoffman. Right there. So this is just a general list right here. Right, but this is like it doesn't go over like the primary unhindered versus primary hindered because it could get more like complicated with some specific examples. But I think this should be most of it here.
Okay, can you bring the bottom one up a little bit so I can see the problems and scenarios?
Yeah. Let me do that. Okay, take a picture of that. Okay. Do you have a picture of the last board?
Yeah.
Okay. That's good.
So the first one,
Mhm.
looks like it's a weak base and strong nucleophile. So
Right.
I'm guessing it's either can go through SN2 or no, it can only go to SN2.
Right. SN2 because what kind of substrate do we have in this structure here? Oh shoot.
We have a
Uh-huh.
negative CN.
Negative CN minus. And primary, secondary, tertiary
As
substrate.
secondary.
Secondary. Right.
Yeah, so that would SN2, that's substitution. So it will replace the BR with the CN.
Yeah. This CN will attack that electrophile, kick out the leaving group.
Versions, I believe, because it's SN2.
Oh yeah, what was the thing you said earlier before that?
Inversions.
Inversion, right. Right. Because of a backside attack mechanism. This CN here will go on the backside and invert that dash into a wedge. That inverts stereochemistry. Right. Let me make this more like accurate because this right here, we don't actually have to draw chiral center, draw wedges and dashes because that's not a chiral center here. Do you know the reason why this is not a chiral center right here?
Yeah, because carbons are identical to each other.
Yeah, these groups are identical to each other. So if that's not a chiral center, we don't have to include wedge or dash. So let me just put methyl group right there. Methyl group right here. Okay, now we can include wedges and dashes.
Oh,
But
okay.
if that wasn't a chiral center, you could just leave it as a flat bond.
Okay.
Uh-huh.
And then
Okay, let's do this one.
one OH, I think is base, a strong, is it a strong? Yeah, a strong base. Because if you use the H, it becomes negative. The O with the negative.
Yeah, so the O with the negative would be a strong base, right? But what would take off the H? There's no other strong base to take off the H. So it will be a neutral ROH. And what is a neutral ROH? Because this O here is not negative, and there's nothing to take that H off to make that O negative. There's no strong base here. So
Okay.
uh-huh.
So
This
it would
is
be a weak base, and yeah. So that would either go through secondary, SN1 or E1.
Yeah, this is going to be SN1 E1 reaction, right? This would be a strong base, strong nucleophile if you see Na there or K there, but that's an H, so that's ROOH. That's not Na or K.
Okay.
Yeah. When you see Na or K there, then that would be a strong base.
Oh, like why is it? Okay.
Yeah, it is because let's say we have CH3, CH2O, let's say Na. You know how earlier we said Na always has a positive charge?
Mm-hmm.
Whatever is attached to that Na is always a negative charge, like that, right? And so when we draw that out, this CH3, CH2O minus is a strong base, strong nucleophile. When we draw this out, this H is not Na or K. That H is bonded to that H right there, that oxygen right there. What is oxygen? Is neutral, no negative charge there, right? And what is stronger base or nucleophile? The neutral O or the negative O?
The stronger is the not neutral one, the other one, because it's really
Negative charge.
positive. Yeah.
Right. Yeah. It's less stable, more reactive, more nucleophilic or more basic, right? And that's from this Na or K, making this oxygen negative. But this H here is not Na, not K. So it is directly bonded to the oxygen, making that oxygen neutral and weak.
Even if the hydrogen is positive, like in terms of the charge, it's also positive.
Yeah, the hydrogen is partial positive, and this oxygen is partial negative.
Oh.
But the full negative charge is still less stable than the partial negative charge. The full
Oh.
negative charge is still more reactive than the partial negative charge.
Oh, okay.
Right. Yeah.
So that would be SN1 or E1. I remember something about SN1 and E1 always happen together, but
Mhm.
I remember something about back when I was learning ochem, it was like
Yeah.
this one. I don't remember which one, but it's always these two that always happen together, but only one of them is stronger than the other one.
Yeah. SN1 is always major over the E1. Unless you have heat, or like you see this delta symbol or triangle, that's heat. And when you see that, E1 would be major over SN1. But usually SN1 is major over E1.
Okay, so
Yeah.
that means that E1 still happen, but it's just get overpowered by the SN1.
Yeah, E1 still happens, but it's overpowered by SN1, where E1 is going to be the minor products, SN1 is going to be the major products.
Okay. So
And let's...
then would it be SN1 then the answer for this?
Yeah, the major product would be SN1 for this here. But do you remember the mechanism of this reaction, SN1 E1? Like what's the very first step of the mechanism that happens here?
For SN1, since it's weak, the I think the Cl it will like remove itself somehow.
Yeah, it just leaves by itself, right? And the
Oh.
reason why it leaves by itself is because you know how we have partial negative, partial positive charges here, right?
Yeah.
This H partial positive charge here will float around the Cl minus and like just grab it away. Like a lot of this will just solve it around it, creating a solvation shell and grab that chlorine away, and that chlorine will just leave by itself.
Oh, okay.
Yeah, it just leaves by itself. That's the very first step, right? And then what do we form here after it leaves by itself? What charge do we form?
After it leaves by itself, let me think. Positive, because Cl is negative. Is that right?
Yeah, this carbon here would be positive, but the reason is because that carbon there lost a bond, right? This carbon here, it used to have 4 bonds, 1, 2, 3, and then the fourth one to an invisible hydrogen. But now it only has 3 bonds, 1, 2, and then 3 to the invisible hydrogen, right? And then if it only has 3 bonds, then that carbon will have a positive charge. Right? And then whenever we have this carbocation intermediate, what do we always have to look out for? What step do we always have to look out for?
That I forgot what it called, but it's like moving, like stability.
Yeah. Carbocation rearrangement, or moving it to a more stable position, right? Which we see it can do that from that position right there. And to do that, we do a hydride shift. It could be a hydride shift or a methyl shift, but in this case, we're going to do a hydride shift here, where that invisible hydrogen right there that I just drew out is going to move and shift to that carbon right there and create this new carbocation right here. It came from a secondary carbocation to a tertiary carbocation, which is more stable through hyperconjugation. And the hydrogen that moved is going to be right there. That's invisible right now, right? Now this carbon here has 4 bonds because it has 2 invisible hydrogens. Before, it only had 1 invisible hydrogen, right? And then from here, right, this weak base, weak nucleophile, the oxygen pair of electrons will attack that carbocation right there and give us this thing here. You know how the oxygen was the attacking atom that attacks that carbon right there? This is the new bond between this carbon and that oxygen right there. This is new between the oxygen attacking atom and that carbon electrophile right there. We still have to draw what's attached to the oxygen, which is a CH2, CH3, and hydrogen right here. What charge would that oxygen have with 3 bonds and a pair of electrons?
3 bond. Positive, because
positive charge. Right. How can we make this positive charge oxygen neutral?
What if you use the OH again to do something, to make it into water or something, right?
Oh, not water, but deprotonate it into ether, OR, right? Because this oxygen here has an acidic hydrogen, where this other ROH can grab that hydrogen right there, and that bond right there that has 2 electrons is going to go onto that oxygen right there.
Oh.
And then that's going to give us this neutral oxygen with 2 pairs of electrons now. Before, it only had 1 pair of electrons, but it gained a new pair of electrons to the oxygen right there. Yeah. See you, Ryan. I'll see you tomorrow. Yeah. Okay, yeah. Right, so this is now our neutral product here. Right, that's our major SN1 product. Right, does this make sense so far?
Yeah.
Yeah.
So
then
does
from-
that mean the OH becomes like it just still the hydrogens on the ether? The OH, that step right there?
Yeah, the hydrogen is gone now. The hydrogen got taken off by that alcohol right there, which would create this side product here. But this is not important right here. Like this other alcohol here gained another hydrogen, which becomes this OH2 plus here.
Okay.
Right. That hydrogen right there got grabbed by that oxygen, which becomes this here. Right.
Oh.
And then when it got grabbed, that bond between the oxygen and hydrogen has 2 electrons, where those 2 electrons will go onto the oxygen right there and make it neutral.
Okay.
Oh, was that your question? Or was it something else? Sorry.
No, that was the questions.
Okay. That's good.
So that would be the byproduct of this whole reactions, that OH2.
Yeah, this would be the byproduct.
Oh.
This would be the main product.
Okay.
There is a minor product here, which is the E1, which we're going to start from here, right? Draw out all the beta hydrogens. We have this beta hydrogen, and this beta hydrogen here, right? Wait, let me try this color. Let me see if it's clear. This is, oh, there you go. See, can you see that? Oh, you can, okay. Which one of these hydrogens, A, B, or C, would give us the most stable double bond for the E1 reactions? Because think of E1 and E2 reactions, they always form double bonds. So which one of these would create the most stable double bond?
The C.
Yeah, the C, right? Where the C is going to be grabbed by this alcohol here and then make a double bond right there. There's no leaving group to kick out, so that's all that happens to form this minor product here. Right, that double bond E1 product right there.
Oh.
So in the red arrow right here, this alcohol acted as a nucleophile for SN1. In this green arrow here, this alcohol acted as a base for E1 because nucleophile attacks electrophile, and we always make a new bond between the nucleophile and electrophile. This is the new bond between the nucleophile and electrophile here, where the nucleophile always attacks the electrophile. The base here would always grab the hydrogen and either give that carbon a negative charge or make a double bond right there to make that neutral, which this did, right? This grabbed the hydrogen right there to be the base. So SN1 eats SN2, nucleophiles are used, E1, E2, bases are used.
Oh.
Right? Because E1, E2, they always make double bonds.
Oh. So that means with the third one, that would be E1 or E2. E2 is a strong base.
Strong base, right? This is Na here.
That's strong base.
Yeah, strong base, and this is K, so this is also strong base. But when we have strong bases, we have to determine if it's a bulky base or a small base.
I think both of them are small because there's only one CH3 attaching to it.
Yeah, this one is the small one. This one is the bulky one.
Oh.
And for this, yeah,
Oh. So why are they bulky when there's only one CH3 coming out of it?
Oh shoot, I forgot to put parentheses 3. There you go.
Okay.
Yeah. That was my typo. Yeah. So this is supposed to be CH3 3C. Okay. Bulky. Yeah, I meant to make that bulky.
Okay.
Uh-huh.
Since the small one, it would go into where's the most stable, which is 1, 2.
Oh, let me. Okay. And let's draw out all the beta hydrogens. Like that.
Just like a quick reminder, alpha hydrogens is if it's right next to a carbonyl, right? And then beta hydrogens is something that
Alpha, beta, gamma, delta, epsilon. Right. This is the carbonyl carbon right here. Oh. Carbonyl carbon. And then alpha carbon is 1 carbon away from the carbonyl carbon. Beta carbon is 2 carbons away. Gamma carbon is 3. Delta is 4. Epsilon is 5. But there's no carbonyl here. So the alpha carbon here is going to be the carbon holding the good leaving group.
Oh,
The beta carbon is 1 away, always 1 away from the alpha carbon. In this case, there's 3 beta carbons.
okay. So
And then
the
this one.
first one, it will go to that first beta hydrogens, that first one, like the top one, because it's most stable over there.
Yeah, make a double bond there, pick out that leaving group, create this double bond. With this double bond here is tetra substituted, because that double bond there has 4 groups attached to it. 1, 2, 3, 4. Yep.
And the bulky one will go either, I'm not sure if it's go either to the beta, that one, the lower one, or the one outside.
Yeah, so let me go over the stability of double bonds for you really quick. The least stable one is going to be that one right there with no groups on it. And then after that is a mono substituted one. There's only 1 group attached to it. And then after that, the di substituted one, there's 3 types of di substituted ones. There's geminal, which is going to be similar stability as in cis, but the trans is more stable than geminal and cis. Right? Geminal meaning that the 2 R groups are coming from the same carbon. Right? Cis, the 2 groups are coming from different carbons of the alkene, but they're on the same side. Trans, the 2 groups are on opposite carbons of the alkene, but they're on opposite side. Geminal, 2 groups, they are on the same carbon. And after that, it's going to be tri. And after that, it's going to be tetra, like that. Okay. So if we make a double bond right there, what kind of double bond would that be? Like if there was a double bond right there.
That would be the primary, that one right next to.
Oh, this one right here?
No, the one to the left.
Oh, this one? Yeah, so
no, this is the one that you were pointing at first.
Yeah, geminal, right. Because the 2 R groups here would come from the same carbon of the alkene. So that's a geminal alkene. What kind of alkene would get formed here?
Oh, that would be
Like
that cis. I don't know what I call it, like the one next to it.
Oh, this one right here?
Oh, is that trans or is?
Yeah, so let me draw out the 2 double bonds for you. Like it could be this one, or it could be this one here, right? And we're looking at What the heck? Let's see. There we go. Okay. So we're looking at this double bond right here. How many groups are attached to this double bond right here?
1, 2, 3.
Yeah, 3. So it's not di-substituted, so we don't think about cis, trans, or geminal. So this is the tri-substituted one. This is di-substituted because there's 2 groups and it's geminal. Which one is more stable here?
The tri.
Yeah, the tri one,
3
right?
group.
But do we want the more stable one or the less stable one if we have a bulky base?
The less stable one, because
Yeah.
you're not really attacking the other one. Because it's too bulky to go in.
Yeah, too bulky to go here. So it would go for the less bulky one, the most available H one here. Okay. So it's not gonna be that one. It's gonna be this one here, which is a di-substituted alkene, specifically geminal.
So in the ranking, where does the bulky base stop at? For the ranking that you have?
For the ranking, it always prefers to go for this one here. Like it prefers to go for always the less stable one. And for the small one, it always prefers to go for the most stable one.
Okay.
Yeah, this ranking one is just to help you decide which one to go for. Okay. You want more practice on this concept or move on to the next one?
We can move on to the next one. I'll just rewatch the YouTube when I'm confused.
Okay.
Because I think Joseph sent me like do you record it and then you post it, right? Yeah, because Joseph and I rewatch it to like remind myself.
And he also sent you the notes, right? To the our last session. Yeah, that's good. I've been screenshotting the notes here, so I'm gonna put that on the PDF file and then I'll send it to Joseph and he'll send it to you too.
Okay, thank you.
Yeah.
Yeah, there's also this one. I'll just share screen with you first and then. Also this one, and I believe is ozanolysis, but then I get confused because of the chair confirmation.
It looks weird, huh? Yeah. Okay, let me go over this with you here. Yeah. It's just the way they put it, like it looks so weird. But you know what the reaction does, right? Like what does ozanolysis do?
It cleaves.
It cleaves the double bond and creates what kind of functional group?
Carboxylic.
Carbonyl.
Carbonyl, right? Carboxylic acid is a type of carbonyl, but we're not going to create carboxylic acids. We're going to create a carbonyl, like either a ketone or an aldehyde. It's only going to be either one of those two, ketone or aldehyde, not carboxylic acid.
I think on the test, a lot of the time they, instead of giving us the reactions right away, they give us like chair confirmations or like just a bunch of words. Like what was it? Like molecular formula or something?
Oh yeah, condensed formula. Yeah.
And then and then we have to like waste time to figure out what is it first.
Yeah, I know. Waste time to figure out what it is. So to practice. Oh my God, this camera. Okay. Oh, can you share your screen again, please? I need to see the thing. Okay. Let's see. Okay, I got it. Okay, so ozanolysis, like you said, it always cleaves the double bond in half. So I'm gonna make that cleavage right here. And we always create carbonyls where the carbonyl is always going to be right in the middle, right? I put oxygens right here where I cut the double bond. Once I make that cut, I'm gonna get something like this. right? Where that was the cut right there before. And then let's draw everything else the same. Does this make sense so far? How I made the cut and then put oxygens in the middle like that? Does this part make sense so far?
Yeah.
Okay. So once we have this, right, I'm gonna say that you know how this is a ring we have right here? Like this whole thing is a ring. Before we had a bicyclic ring, meaning that there were two rings in this molecule here. The first ring was this part right here. The second ring was like this triangle thing right there. Like, do you see like that? How this is just a bicyclic ring? Like how there's two rings in this molecule?
Oh,
Like there's two rings within this molecule here. One ring is like this part right here. The other ring is that ring right
Yeah.
here. Uh-huh.
okay.
But
yeah.
then when I made this cut, right, that's no longer a ring because you know how that was a ring before, but I made that cut. It's now linear.
Yeah.
We only have one ring now, which this is just going to be a cyclic molecule, a monocyclic molecule, where there's only one ring now, which is this one ring right here. Does that make sense so far?
Yeah.
Right. So I'm gonna say this is gonna be 1, 2, 3, 4, 5, 6. We have a 6-membered ring. Right. So I'm just gonna redraw that 6-membered ring out like this, which is gonna be 1, 2, 3, 4, 5, 6. Right. Where this is an aldehyde because that carbon there has a hydrogen, which I'm just going to draw out to show that that's an aldehyde. And this is also an aldehyde, which we have two aldehydes on carbons 2 and 6. So let's draw that aldehyde out at 2 and 6. Right, so that's the answer. They might give it to you in some rotated version, but that's the answer right there.
Mm.
The hardest part of this problem is redrawing this weird looking structure into this regular bone line form right here. That's the hardest part, like the representation of this molecule. But you get the reaction principles already. Like it cuts the double bond, it creates the carbonyl. They just made it trickier by making it look weird.
Okay.
Like this is the exact same thing as that. It's just redrawn. Oh yeah. Are you okay with me posting the recording of the session on public, or do you prefer to be unlisted?
Oh, no, I don't mind.
Okay.
Wait, but Tiffany, since you talked about the DAT, it should be unlisted, or else you're gonna get your score avoided.
What? Really? But
Like if you talk about the DAT at all in any capacity.
oh,
Oh,
really?
maybe after DAT or still no?
Still no.
Still no.
Maybe
Okay.
it's not the act.
So next time just don't talk about the DAT.
Okay. How about this one? How about this recording here? Yeah, we didn't talk about any DAT at all.
I think we can as long as we don't mention the DAT,
Okay.
right? Because
Yeah.
so we just have to not mention it in the
Yeah,
free.
so just have to
Yeah. Okay.
Yeah.
Okay. No more.
Okay. Okay, yeah, so does it so when I share screen you can't see it, right? So it's fine.
Yeah, you could share screen. Yeah. What like what do you mean? Like I can't see it, like, or the recording?
Yeah, it is the recording. Can it see the share screen practice test?
Oh, it can, but I can edit it out if you want me to edit it out before I
Okay,
post
yeah.
it.
or I can make a group chat on Discord and then you could just send your screenshots there.
You
Maybe?
can't take
Yeah.
screenshot though, because I took screenshot before and they're like, oh well, we're gonna flag you.
Oh yeah.
what?
Oh yeah, true. No. On well I may be able to screenshot on my desktop.
Can you do it?
Hmm.
Because I did it before and then they flagged.
Yeah, it said like you can't screenshot or something like that, right?
Yeah, you can screenshot it.
Because I'm not screenshotting the full screen. I'm only screenshotting like one portion of it.
Okay, see if it flagged you or something because it did that to me before and I was like,
No, it doesn't because I screenshot so many things.
oh my God. Okay, I'm on practice test 1, question 26, if you can screenshot that. Oh, I can just like continue sharing screen until like, because we already did it, so let me as
Yeah,
well.
we already did it, so just keep doing it.
We can just not do it next time, but whatever.
Yeah.
So for this one, is that like a,
Mhm.
if it's N3, is that like a SN? No. Is it E2? E2?
Yeah, so E2 would be strong base, strong nucleophile, which is going to be a negative charge on oxygen or nitrogen. We have no, oh wait, we do. We do have a nitrogen. So that's the exception right there, right? When you see N3 minus, even though that's a nitrogen minus, that's going to be one of the weak base strong nucleophile lists that I give you, like NaCN or NaN3. Think of that as SN2, right? Like N3 minus, think of that as a weak base strong nucleophile. So that's the exception for the strong base right there.
Oh,
Yeah, N3.
okay.
Mhm.
So
So
this
N3,
would go to E, no. So it's an exception for strong base. So it will be weak base, and if it's weak base, it will go through E1 or
if it's a
SN.
weak base, weak nucleophile. But there is another thing that is a weak base strong nucleophile. This is a weak base strong nucleophile. And what reaction does it go through if it's a weak base strong nucleophile?
Weak base, strong. SN2.
SN2, yeah. And then for
I keep
SN2,
trying to remember this because I
yeah.
keep getting confused.
Yeah. You have to like recognize the reagent. That's the memorization part. Like the N3, if that's a weak base strong nucleophile, that's the memorization part. And also you can also understand it as well because if I draw out N3, like this, let's say. Oh, N3. What is N3?
Tiffany, I just realized for booster,
What?
we have a 1-day extension for free because we reach 100 hours. If we reach 200 hours, then we get another day for free. And then if we reach 10-day daily warm-up streak, that's another day, 30-day warm-up streak, that's another day, and 50-day, that's another day.
So we have 100 hours.
Yeah, right now we have 100 and we're
It's 10 for 1
82%
day.
away from, or currently we are 82% to 200, but I don't think we're gonna
Okay,
make
do
it.
more warm up.
No, but so the person contacted me again saying, we could claim this 1 day for free, and then once we do that, we would, or I would send them a screenshot of my DAT confirmation date, and then they could give the rest of the 7 days for free.
Okay, send that then. And you better
So
move it then.
July 8th. July 8th, that's coming up in like
You can't back out yourself if you send that.
2 weeks.
Okay, should I stop sharing screen?
Yeah. So this is N3 right here, where we have 3 nitrogens. 2 of them have a negative charge, 1 of them has a positive charge. But you notice how like this can do resonance by going down here, moving that there. Same thing as over here. This can go down there, move that over there. More resonance, more stable. That's why, since it's more stable, it's a weaker base. But if we have something like this, can this negative charge do resonance on the nitrogen or no?
No,
Yeah, no resonance. Does that make it more or less stable?
less stable.
Yeah. And if it's less stable, is it more or less basic?
Less stable than less basic. Like the
Right. So,
conjugate acid?
like this whole thing in general, like the negative charge here, if it's less stable, is it more or less reactive if it's less stable? Like don't think about the conjugate acid. Think of this whole molecule as it is right now. Like if
it's
it's
less stable, then it will be
yeah.
more reactive.
Yeah, more reactive. And if it's more reactive, it is more basic.
Oh,
Right. So that's why usually nitrogen with negative charge is a strong base, strong nucleophile, because the negative charge there is not stable because it can't do resonance. But the exception here that I talked about is the N3, right? Because the N3 minus, there are negative charges on the nitrogen, but we say that the negative charge on the nitrogen can do resonance, right? Making it more stable, less basic, less reactive.
okay.
Which prefers to go for the SN2 reaction, which does a back side attack, and it inverts stereochemistry. So that was the question on your DAT, where it inverted the stereochemistry, and then that changes the RNS configuration chirality, right? Are you familiar with identifying chiral centers and assigning RNS to those chiral centers?
Yeah, but it takes me a while. Like I need to kind of know how to do it quick. Is that
Yeah, I could show you a shortcut maybe. I'll show you how I do it, and then maybe that'll be
okay?
faster. Yeah,
Yeah,
can
because
you?
I usually do the numbering and then switch it around and everything, but that takes forever.
Oh yeah, like rotating and everything and stuff like that.
Yeah.
Yeah. There's different examples too. Like some examples take like are faster than other examples. If the lowest priority group is already in the back, then that's the fastest example. If the lowest priority group is on a wedge, then that's the second fastest example where you just flip it at the end. The slowest example is the one where the lowest priority group is on a bond line form, not a wedge, not a dash, where you have to like rotate the groups.
Oh, that. Oh, if I have that, I think I'm gonna get that wrong.
No, I can show you that example here. Have you ever seen that in the DAT practice before or DAT exam, like the one where the lowest priority group was on the flat bond?
No, but then I'm known for like having the worst luck. So
Oh yeah. Let's just go over it. Let's just go over it just in case.
yeah.
Uh-huh. Okay, first let's go over your DAT question. And then
Well,
for next time, right? Or actually, no, I don't know. I'm not sure. Maybe I was gonna say maybe we could be in person, but like I'm gonna start my like chiropractic school soon, and like you guys have the DAT
oh,
soon,
you
so we'll see.
starting? Oh, when are you starting your school?
Orientation is July 5th. The first day is July 8th. So if you guys are free, like next week, we could do in-person session at like some library with the whiteboards if they have any. Or yeah.
Okay. I don't think the library has any whiteboard for besides the SJSU one, but then that's kind of like you have to pay for parking and everything.
Yeah. The previous one doesn't have any rooms with whiteboards.
They have room, but then they don't have like I don't think they offer whiteboard.
I
Yes.
see.
Mm. It might actually. I don't know. I'm not sure. I haven't booked a room yet, but let me take a look tomorrow.
Okay. Oh yeah. Did you go there often to study, like for the DAT or your work or your schoolwork? The Wilfridas Library?
I go every other day to take my test. So yesterday I took
Oh,
my test for practice test, and then today
yeah.
I'm going over like everything that I'm still confusing on, and then tomorrow I'm gonna take the test again.
Oh, so you take it every other day, the DAT?
Yeah.
Oh, so that's like 3-4 hours? How long is it usually?
Like 5 hours.
Oh my God. And
Yeah.
Joseph, he procrastinate, he party all day, he stay
Joseph, what have you been doing? But let me share the screen of the. So this one, I think they already have it, and no, you gotta switch it.
Yeah, we have to switch it. Okay, I'm gonna go over that example and then 2 other cases where you might see on the DAT as well. Right? Okay. Okay, I got it.
Okay.
So the example they gave you is the intermediate level one, the one that takes the second fastest. Or actually, the way it's given, it was intermediate, and then they flip it to the easiest one.
Oh,
I'll show you. Well, this is actually testing a lot of concepts, this question here. Right? It's testing if you can recognize what reaction it is. Is it SN2, SN1, E1, E2? And then once you do that, can you assign RNS? Can you find the chiral center and stuff like that? And like also the mechanism of SN2, backside attack, inversion, and stereochemistry. So yeah, there are a lot of concepts tested in this question here. N3 minus, that is weak base, strong nucleophile, SN2, good leaving group, secondary substrate, because it's 1 into 2 other carbons. First, let's do the reaction. This N3 minus here will attack that electrophile, kick out the leaving group, and do a backside attack, inverting the stereochemistry. So that dash will get inverted into a wedge like that and become N3. And this hydrogen here will become flipped as well. Right? This is a chiral center because there are 4 different groups attached to it. 4 different groups, which is a methyl, ethyl, N3, and H. That's 4 different groups attached to it. Right? Now, to assign priority, look at the very, very first atom attached to the chiral center. The highest priority, we have the one with the highest atomic number, which is going to be nitrogen here. The lowest priority group is going to be hydrogen because that has the lowest atomic number. But we have a tie here. We have a tie between this carbon and carbon because that's the same exact atom. If we have a tie, then we have to see what's attached to that atom. This carbon here is attached to 1 carbon and 2 hydrogens. This carbon here is attached to 3 hydrogens. Right? So now we compare the atomic number. Did I say atomic size before? Like to assign priority? Or did I say atomic number?
you said number.
Okay, good. It's comparing atomic number, not atomic size. Right? The one with the higher atomic number, we have the higher atomic, higher priority, which is carbon in this case. So this is number 2, and then this is number 3. Right? And then for R and S, we always want the lowest priority group 4 to be on the backside, the dash, which is good in this case. So we don't have to do any rotation or flips. And then when we rotate it, I ignore the 4 and I just go 1, 2, 3, 1, 2, 3, like that. Right? And then if I see it going to the right side, clockwise, then that is R.
Yeah. Okay. So besides like numbering it, is there any way that you do that make it like really quick? Besides just like maybe practice more or something?
Yeah, because you can just practice more and then you could like look at it, 1, 2, 3, right, and then R right away. Like the more you practice to do, the more you can see it and do it in your head and like just do all this stuff without like writing it all down. Right.
Okay.
And let me give you one, and then you try doing it in your head and tell me what it is.
Oh no.
Okay, try this one in your head.
That all. S.
Yeah, S. 1, 2, 3. And I already know 4 is on the back side, so that's good. We don't have to do anything else. 1, 2, 3. Going to the left side. S. Yeah, you got it.
And then what was the one that you were like the hard one? Where's
Yeah. Let me show you the second the second easy one first, and then the hard one after that.
okay.
Yeah, because this is the easiest one right here, where the lowest priority group is already in the dash, where we don't have to do anything. That's the easiest one. Okay. So let's say you notice how the lowest priority group is on a wedge.
Yeah.
If it's on the wedge, then there's a shortcut to find the correct answer. You do everything normally, and then you just flip at the very end. That's all you do for this example here, right? That's why it's harder than the first one, because yeah, you have to remember to flip it at the end. For the first one, we don't have to flip anything because the lowest priority group is already on a dash. But if it's on a wedge, then we have to flip it at the end. So do it normally first. Like, would this be R or S from this structure here?
Will be S.
Oh, nice. Wait, 1, 2, 3. Going this way. Yes, yeah, nice. You can just do it in your head now, right? But then, is that the actual answer or no?
No, you have to flip it.
We have to flip it because the lowest priority group is not a dash; it's a wedge. 4 on wedge. Then you have to flip it. That's the second example, the one that's harder than the one we did last time.
Yeah.
Now, the hardest example is going to be the one where the lowest priority group is on a bond line form. And that's where you have to like actually rotate the group, and you can't flip it at the end. You have to actually rotate it. Right. Sorry. Okay, let's say we have something like this. The very first thing you do is recognize your lowest priority group, which is that H right there, and it's not a wedge or a dash. If it was a dash, you do everything normally, don't flip anything, that's the right answer. If it's a wedge, you do everything normally, you flip at the end to get your answer. If the lowest priority group is not a wedge, not a dash, you can't do that, right? You have to rotate these groups. Oh wait, this has to be one that's dash. If that's wedge, this has to be dash. Okay. So look at your other flat bond line form right there. Keep that stationary and still. And we're going to rotate these 3 groups right here. That hydrogen, that methyl, and this alcohol right here. We only want to rotate it once to make the lowest priority group on a dash. So to rotate it once and make it into a dash, do we want to rotate it this way or the other way?
The other one. This
way, right? Where the H will become a dash, this dash methyl will become a wedge, this wedge OH will become a flat bond like that. After we rotate everything, keeping this ethyl group the same, that stays the same. The dash is now a hydrogen, the wedge is now a methyl, and then the flat bond is now an OH. Right, now figure out if it's R or S from here. We just converted the hardest example into the easiest example here, where the H, or the lowest priority group, it doesn't have to be H, is on the dash.
I forgot if it matters if the highest priority has to be on the wedge or not.
No, it doesn't matter. The only thing that matters is the lowest priority group has to be
Okay.
on the backside, the dash. The highest priority group, it could be a flat bond, it could be a wedge, it doesn't matter.
Okay. So now it would be 1, 2, 1, 2, 3, 4. So that is S.
Yes, yeah, you got it.
Okay.
Thanks.
And okay, this is off the topic for this, but you know how when they give you like two different structures, and then they're like, oh, I always get confused if it's identical or if it's enantiomer.
Yeah, identical or enantiomers, like isomers, stereoisomers, or diastereomers, something like that.
Yeah, because sometimes it looks like it flipped everything, but then they did some like rotating and everything, and then it's like,
rotating
okay,
and flipping.
one.
Yeah, and it says it's identical, right? Like sometimes.
Yeah. So like this one I got it wrong because I thought it was like an enantiomer because it's like changing from wedge to dash everything,
Yeah.
and it turns out identical.
Identical, yeah. Let's go over that. Let's go over the stereoisomers as well,
Do you
because
need
that could be
an example
tricky.
of this?
Yeah. Let me. I can make up examples of it. Unless
Okay.
you have an example, we can go over that example if you have an
That's
example of that.
okay. Because I need kind of like new problems anyways.
Okay. Yeah. Okay. So stereoisomers, there's going to be a lot of types actually. Right. I'm going to show you the safe way to get the right answer every single time, and then I'm going to show you the risky way to get the right answer. But it takes like it's high risk, high reward, because if you do that way, then you save a lot of time, and then you could get the right answer. But like it's more risky because you get the wrong answer as well, where you have to do like some mental gymnastics in your brain, like flipping it, rotating it, and then guessing. Like not guessing. Like if you know it, then you know it. But there's another way that it's 100%, like all the time. But that takes a longer time to do it. I'll show you the longer way, and then I'll show you the risky way afterwards. Right. So stereoisomers, there's different types. There's regioisomers. And there's stereoisomers. Right. There's only one regioisomer I can think of right now, which is going to be constitutional isomers. Constitutional isomers. The stereoisomers, they could be enantiomers, diastereomers, or meso. Identical is like not a stereoisomer at all, because the identical is just the exact same thing, exact same molecule. Right. So all of this here, the thing that you have to look out for is the R and S of all chiral centers. Look at the R, S of all chiral centers. If no change happens to any chiral center, right? Like all the chiral centers stay as R, or all the chiral centers stay as S, then they're identical. That's the 100% way to do it. Look at all the chiral centers, assign R and S to them for both molecules, and then if it's the same, then they're identical. If all R and S flip, then they are enantiomers. Like if you have one chiral center only in a molecule, and then the other molecule has like that same chiral center, but it's like S and instead of R, then they're enantiomers. But if you have two chiral centers, like let's say RS and then the other one is SR, everything flip, then that's enantiomers. For diastereomers, it's only some flip, some stay the same, right? Like for example, if you have two chiral centers, RS, and then the other molecule is RR, then only one chiral center changed, but one stayed the same. That's diastereomers. For meso, this is most likely two chiral centers where one is R, one is S, and then you have a plane of symmetry. That's the most important thing. Plane of symmetry. Okay. And then regioisomers, constitutional isomers, is just going to be same chemical formula, different connectivity. Right. So let's look at some examples here. Let's say we have this here, these two molecules. Would these be identical, constitutional, enantiomers, diastereomers, or meso molecules?
I think this have to do the RNS thing. One, two, so the first one, BR, so 1, 2, 1, 2, 3, 4. Okay, so the BR for the first one is R.
Nice, nice.
Second one is 1, 2, 3, 4. Is R, but it become S because
Yeah. Right. Because the lowest parity group is on a wedge, and you have to flip it at the end.
1, 2, 3. It's S, but then it becomes R. So,
Yeah.
that one, yeah.
Right.
1, 2, 1, 2, 3, 4. So that's S. Yeah, and it stay S. Right? Yeah.
Yeah. It's S and it stay S because the lowest parity group is on a dash. So it will stay S like that.
So this would be identical.
Identical because the R stay as R, the S stay as S. Right? I think on the DAT, you said this was enantiomers because you saw the wedge got converted to dash, and then the dash got converted to wedge, and then you think everything changed and that's enantiomers, right? But that's not the case here. That's like, this is the safe way, RNS. Look at the RNS of everything.
Okay. Now, what about the risky way?
The risky way? Yeah, so
yeah.
the risky way here is like, you know how the bond line form, it starts down and then it goes up and then like down, up, like that?
Yeah.
And this one here, it starts up and it goes down, up, down, like that, right? So imagine this whole thing flipped upside down like that, right? So look at this marker right here. You know how a wedge shows that it's going towards you like that? Like that's going towards you, like towards the camera, a wedge, right? If I flip it upside down, now it's going away from you, away from the camera.
Oh.
Right? Because you know how to get this bond line form here, to get to this form, we can just flip it upside down to like get this down up to become up down. If I flip it upside down, that flips the wedge to a dash like that as well.
Oh, because the dash is going into the page and the wedge is going at you?
Yeah, the wedge is going at you, the dash is going into the page.
Oh.
Right? And then if I flip it upside down like that, that would flip this whole bond line form as well, where it's not going to go down, up anymore. It's going to go up, down, because like see, I have a model kit here. I could like try showing it to you. Let me try to build this really quick. See. Let's see, this is carbon. That's 4. Let's see. Well, carbon is black. White is hydrogen. So that's the one. One. All right, I want a single bond, so I want this one. Yeah, so this is gonna be 6. Okay. So that's last one. Yeah. Okay. I'm not gonna put the hydrogens in because that's way too many hydrogens. But I will put the bromine and alcohol. So the bromine is going to be, where is that bromine? Halogen. I mean green. Okay. So on carbon 2, and that's going towards you. So I'm gonna put it in front of the camera to show that it's a wedge. This green is the bromine, the halogen. And then carbon 3, oxygen. Oxygen is red. So that's gonna go away from you. So I'm gonna put that oxygen away from you like this, right? So the black ones are carbons. The green one is the halogen or bromine. And then the red one is the alcohol, right? Let me make it go down, up, and then make it accurate to how I drew it on the whiteboard by putting this here. Okay. And this one should go right here. Yeah. So you know how this is down, up, just like this is down, up, down, up.
Yeah.
And then this bromine here is a wedge going towards you. So that's going towards you. This alcohol here is going away from you, dash away from you. If I want to flip it to make this go up, like right now, this is down. If I flip it upside down like that, you know how it's up now?
Oh, yeah.
Right? If I do that, right, you notice where the bromine is now on the backside away from you. The alcohol is now towards you, towards the camera. Right? Where the alcohol towards the camera is the carbon next to it is going down, going down, going down. Like that. But if I do this, where the alcohol is now away from you, the carbon next to it is going up. Away from you, carbon to it is going up. It's the exact same thing though. Like this is the exact same structure. It's just flipped and rotated like that, which is drawn like that. This is just flipped. Right? Where that is the identical structure. They're the exact same thing. They're not enantiomers, because if they were enantiomers, then like the connectivity, like the spatial rearrangement would be different. But I didn't change anything. I just flipped it, rotated it, and stuff like that, which is the exact same thing. That's the risky way, like thinking of the rotation and flipping thing in your head.
Yeah, I think that one I need more practice. Like, yeah.
Yeah, for the DAT, just do the RNS. Like, find all the chiral centers, do the RNS, and then if it's all the same, identical, if everything changed enantiomers, some change, some stay the same diastereomer, I think that's good for DAT. Like this one, it would save time, but it's more risky.
Yeah, and yeah.
Right? Because can you see it? Like if you flip it upside down like that, like you just get like this thing here.
Yeah, I can see it, but I feel like the process of me imagining it is
Mhm.
already like taking more time than like giving it RNS.
Oh
Yeah, because
yeah.
I'm not used to it.
Right. So stick with RNS. Like yeah, don't do the risky route. Because that's probably gonna take more time. Just to think about it and be sure, you know.
Yeah.
Yeah.
I think I have like one more question.
Mhm. Yeah. One more session, and then I'll stop the recording.
Okay. So this is the last questions. I'm not sure what I mean, I know what they asking, but then I was confused when I saw like the neutral pH and then the low pH, and I was like, oh, what?
Oh, which of the following compounds is insoluble in water at a neutral pH, but is most soluble at a low pH? Oh, okay. Let's go over this question. Oh, keep the camera on, and I'll put it on the board. Oh wait, let me screenshot this so I can send it to you guys after. Wait, yeah, actually, stop sharing for a little bit so I can screenshot this. Yeah, thank you. Okay. Okay. You can share screen.
Oh.
Okay. Insoluble in water at, let's say, pH around 7.
You want me to still sharing screen?
Yes, please. And low pH. What does it mean for a solution to be low pH? Is it going to be acidic or basic?
Acidic.
Yeah, acidic conditions.
And neutral is just neutral.
Yeah, no acidic, no basic. And let's do A, B, C, D, E. I'm not going to draw out the condensed formula. I'm going to draw out the actual bond line form. C6H5OH, that's phenol. Benzene with alcohol, CH3, CH2, 1, 2, 3, 4, 1, 2, 3, 4, 5. Right. Pentanoic acid. C is CH3, CO, CH3. That's an ester. Benzaldehyde for D. And then for E, aniline. Okay, you can stop sharing. Okay. So this is what the structures would look like at a neutral pH. Nothing's going to deprotonate it. Nothing's going to protonate it because we're not in acidic or basic conditions. Right. So let's first eliminate the answer choices that would not follow through with this point here. Insoluble in water at a pH of 7. Right. Insoluble. Okay. Yeah. So what this is going to ask for is like, will it get deprotonated by itself in water? Phenol here, right? It's not going to get deprotonated in water. So that is, let's see, insoluble in water at pH 7, neutral, soluble at low pH acidic conditions. We could get rid of B right away because you know how B is a carboxylic acid, which is a very strong acid? When it's in water, it can get deprotonated and become this carboxylate here. It's very soluble in water. Carboxylic acid is very soluble, so we get rid of B right away. Let's see, insoluble in low pH conditions. Let's see. Wait, can I see the answer choices again? I want to make sure I get this right because like I see like multiple correct answers here for some reason.
Okay.
Yeah.
Wait.
Okay. C6H5 NH2 phenylbenzaldehyde aniline AD are insoluble in water. AD insoluble in water. C benzene tenoic acid. So okay. They're saying that esters are slightly soluble in water because they can do H bonds with that carbonyl oxygen right there. So that is going to be soluble in water. So we get rid of that option choice because this partial negative oxygen here is attracted to this partial positive hydrogen of water here. Right. This partial negative oxygen is attracted to this partial positive hydrogen, H bond. And if there's H bonds in water, then it's soluble in water, not insoluble in water. This carboxylic acid is insoluble in water because it is very strong acid. It just gets deprotonated. A, D, and E are insoluble in water. Okay. Can you share your screen again? I want to see like why they said this is soluble in low pH, but why this is not soluble in low pH. Let's see. Aniline is different from the other options because the amine group can act as a base in low pH. When it becomes protonated in acid, aniline is in a positive charge and enhances the stability better. Okay, option A is incorrect because hydroxyl group is not basic as an amine. Oh, okay, there are multiple correct answers, but one is just more correct than the other. That makes more sense. Okay, C is incorrect because esters. And then B, C. Okay, I got it now. Yeah, you can stop sharing your screen now. Okay, so does this make sense so far? Why I crossed out B? It's because it's insoluble in water. Because this is a very strong acid, which just gets deprotonated by itself to become carboxylate here. Does that make sense so far? Why I crossed that option out?
Yeah.
Yeah. And then for C, right? You know how I said the carbonyl oxygen here can do H bonds with the water? Does that make sense so far? Like why that's also insoluble in water? That's not correct because it's soluble in water because it can do H bonds. H bond, acid. These are soluble in water. That's why these are wrong because this is an acid soluble in water. This can H bond with the carbonyl oxygen soluble in water. So that's why I got rid of it because it's not insoluble. Does that make sense so far?
Yeah.
Yeah. That's the same reasoning for D as well.
Oh, because the
D.
carbonyl?
Yeah, because the carbonyl. Right? D has a carbonyl, C has a carbonyl. It can also do H bonds as well, which is also soluble in water. Right? There's no carbonyl in E, no carbonyl in A. So they are insoluble in water. Right? Now this is the part where I was confused about because at low pH, it was very vague, right? Because like OH and NH can get protonated. Because you know how at low pH we said is acidic conditions?
Yeah.
The acidic conditions, what do you think acidic conditions would do to these atoms here with pairs of electrons? Like what would happen to those atoms there in acidic conditions? Like let's say we have H2SO4.
Protonated because there's
Yeah.
H plus flowing around and stuff like that, right?
Yeah. It doesn't have H2SO4, it could be H3O plus, any H plus source, right? Protonated. Both of those can actually get protonated if we're at a low pH, but there is something that will get protonated first, right? Because what is the more basic atom? And what's the factor? Like what's more basic? A nitrogen or an oxygen, and why?
The nitrogen because the oxygens is very electronegative.
Yeah. This is less basic because more electronegative. This is more basic because this is less electronegative, more willing to give up electrons and attack the H. That gets protonated first.
Oh,
Yeah.
so that's why it's soluble in low pH because it's more willing to attack and
Yeah, more willing to attack. But if we keep decreasing the pH, right, becoming more acidic and acidic, this would also get protonated, but this would get protonated first before this.
Oh, okay. So
If they're in the same solution, this would get protonated first.
which one is a more correct answer?
Yeah, this is the more correct answer. These should actually both be correct because, like, they would both be soluble in water. This would be soluble and this would be soluble in water. But this is more soluble in water because it's more basic.
Oh, okay.
Yeah, this is more correct. That's why I got confused. I was like, huh? Like they should both be soluble. I think the question would be better if they asked like, which one would be like more soluble, which one would be more basic, which would get protonated first, something like that. But if they just say soluble, then I would say A and E are both soluble, but E is more soluble because it's more basic. Right? Does that make sense so far?
Yeah.
Okay, that's good. Okay, I'll screenshot this.
Other questions. And yeah. And I have to go now because
Yeah.
I have to go right now because I have to pick up my brother at the airport. But
Oh,
thank you
okay.
so much for
Yeah.
today. Thank you.
No problem. No
I'll ask
problem. Worry.
Joseph for the recording and the notes. Thank
Yeah.
you.
Yeah, no problem, Tiffany.
Joseph,
See ya.
he's gone the whole time. What the heck, Joseph?
Yeah, what was Joseph doing?
I don't know. He was drinking coffee or something. He was. What were you doing?
Oh, he was drinking coffee like this? And he was reacting
Yeah, he was
coffee?
like that.
Okay, to be honest, I wasn't really paying attention this time because I was planning on watching the recording.
Oh, I see.
But the first time, the first session, I paid attention.
Yeah. That's good. And next session, maybe meet up in person or something? I don't know, maybe.
Tomorrow.
Tomorrow I'm
have
taking a test, but then I can do Friday because I do it every other day because I won't have questions tomorrow. But if Joseph has,
But we could just like work on the practice tests, like the ones that you haven't done already. Like we could just do it together.
oh, okay.
well, let's see. Well, I have private tutoring 2:30 to 3:30 and then 3:40 to 4:40. So I won't be free that time. But I also
So
have private
maybe
tutoring
next time.
Friday. Are you guys free Thursday? Oh no. Oh wait. Oh yeah. Are you guys free Thursday? Yeah, I guess free Thursday.
Thursday I can do it, but
Thursday I could do after 1.
okay, yeah, that's fine.
Sounds good. Okay. Yeah.
Wait,
that works
just
with me.
kidding. I think I'm eating out with my internship stuff.